Good night, everybody. On the behalf of the postgraduate program of Material Science and Engineering here from UFABC, I would like to welcome Dr. Adam Duong.
Hello.
Dr. Duong is going to talk about advanced materials for energy conversion and storage approaching the future. So, Dr. Duong, please feel free to start your talk, and it's a pleasure to have you here.
Okay. Thank you, Anne. I'm going to start to share my screen and we can talk about that. So good good evening, UFABC. You see, I'm a little bit like is at what time they are here. Good afternoon, UFABC. Good afternoon, UQTR. Thank you so much to join my presentations and welcome everyone to the seminar of the graduate programs in material science and engineering at UFABC. Thank you, Anne, for this introductions and to invite me to give a talk. As Anne was saying, today I'm going to talk about advanced materials for energy conversions and storage approaching the future. So first of all, I am going to give an overview about the challenge of energy conversions and storage. Then I'm going to briefly talk about the scientific approach and especially the work that we are conducting in the Jung Lab. I'm going to include the environment work that we have at the Université du Québec at Trois-Rivières. There's so many work that is going on in my team that I will not be able to show everything. So what I decide to do is to give only the two, let's say, only two projects that I'm conducting currently with my student. The first one will be about the hydrogen productions by photocatalysis. And the second one will be the approach how to design porous materials that can be useful for gas separations and storage. Finally, I'm going to give a brief conclusion and the perspective of the work related to energy. So, with the depletions of the fossil fuels, the need to find other energy source is becoming urgent. Energy is at the heart of our concern, actually. Energy forms the very backbones of us and the entire world. For example, you see these players, if he want to run fast, to have a good control on the ball, then and to push the ball actually in the goal, like Neymar, we need to have a very good control on the ball, have a good speed that nobody can catch him, but he also need to be very skillful, right? So to have this skills on, he need to to train a lot, but he need also power. So where this power come from? Here's a very short scheme is showing to you how the sunlight it convert to hail, and the hail is eat by the cow, and then with the milk that the cow is producing, we can make cheese and food and so on, and then the player will have power to do what he is supposed to do. But food is not the only concern that we have. We also need energy for our domestic house. I was trying to find the value in kilowatt hour per years. I found that in Canada, an average for a house, it's approximately, let's say, 11,000 kilowatt hour per year. and in Brazil it's only 1,800 kilowatt hour per year. I guess this is due to the fact that our winter it's very hard, so then we need to heat more our house, so on. So we need energy for house, but you also need to communicate, right? So you have also you are going also to spend energy by for the communications on the phone. You also need energy to cook your food, and sometime when we have time and we have some reserve of money, we can also take vacations and take the airplane, and this also costs energy. So in overall, in the world, we need approximately 14 terawatts per year of energy, and this corresponds approximately, if we compare the type of energy, to 14,000 nuclear reactors. For students, I would like just to remind them what is the cycle, let's say, from production to the consumptions of energy. We have on the Earth several primary energy sources, such as fossil fuels, nuclear, and renewable energy. After this, we have to transform the primary energy source to a carrier like electricity, hydrogen, heat, and then now this energy we can use it. We can use or directly for our transportations, for house, and all the activity that I already showed to you in the previous slides. But we can also, and we have also, we need also some time to store the energy, you know, for the harder day, let's say. And then we have to find a way how to store the energy and how to restitute it without losing the energy. So during these presentations, I'm going to try to focus to the one key point is that the efficiency of energy conversions and storage depend upon the material you use it. And I will try to explain this sentence along of my presentations. So let's first take a very simple example. You know, okay, to turn on these small bulbs here, you will need approximately between 2 and 8 joule if it's small bulb, that it's simple bulb. Okay, so then you have to produce 100 joule of using the primary energy, and this energy will be converted to electricity and will be transported, and then you can use this bulb. So you can ask me, okay, where is here we have 100 and here we only need 2 to 8 joule. But however, you have to understand that during the transportations, you are losing energy. And also when the bulb is turning on, you are losing also energy in the form of heat. So for, remember, approximately 100 joule of primary energy will can help you to turn on a light with a bulb of 2 to 8 joule. Let me show you also another example. And in this case, I am going to show you like a chain of conversions and the utilizations of this energy. Let's take the example of the solar cells. The solar can convert the solar cell can convert into electricity, but the yield, the efficiency, let's say, is only approximately about 20%. So you can only transform and have only a part of the full energy that you collect from the sunlight. After that, you will take this electricity and to do the water electrolysis, you know, to produce hydrogen, because hydrogen, I already told you, is one of the energetic vector, interesting energetic vector. But this process only it's efficient, 70% efficient. Then after that, because it's a gas, so then what you have to do is to compress this gas to store this gas somewhere, and then you would be able to use in the future. But this also, because you are taking so much energy to compress the gas, so then we would consider that the efficiency is only 40% because you have to remove the energy you spend to compress hydrogen. Finally, you can develop this kind of technology that is already known. It's called fuel cells. And then you can use it, put this in a car, and then make your car move. So for student, if you have time, you can really calculate quickly, and you will see that the efficiency it's not that high, and you are losing a lot of energy. So these two examples should inform you that okay, there's something that we have to do related to the conversions of energy and to the storage. So that is the point of my presentation actually. But before I start going deeper, I just want to show you here a pie that is showing the distributions on how we use our energy. So approximately 82% of the energy that we use is come from fossil fuel, natural gas, coal, oil, and only approximately less than 15% come from nuclear and non-fossil resources. But there is a small portion that is really interesting, but however is only less than 4% of the energy that we can use is the renewable energy. When I say renewable energy, I'm talking about, for example, solar, wind, geothermal, hydro, biomass, and there's few others, but this is the main category, let's say. Why this energy? They looks like free, but we are not really capable to fully use it, and this is also related to the way how we convert this energy and the way how we can store this energy. So the factor is that because we are not capable to do these two process perfectly well, the yield, let's say the percentage of the use of this renewable energy, it's low. Um, the scheme here I showed to you is just mainly to show to you what is the advantage, why we have an advantage to use renewable energy. Why? Because it's infinite, it's continuous energy, means that okay, sometimes you have a cloud that is a front, let's say, of the sun, but when there is no cloud, you can use it again. And also those energy, they are non-pollutant compared to the non-renewable energy. We have only a limited quantities. It takes time to be replenished, and currently it's cause global warming. So thus we have to figure out what to do to use more renewable energy. But before you do those, let's say, research activity, you have to be aware about several points. And I'm trying here to raise few questions to help you to think about energy. So the first question is, what are our chances to meet the energy demand by 2050? Because by 2050, the population will increase, then we will need much more energy than what we need now. And also, what are the key factor that we need to consider? What are the key factors that will help us to reach our target, for example? And what should we do to reach the demand and the demand in energy? And also, what are the risks? We might change the the, the environment, so on. So we have to take care about this as a scientist. And are we going to find solutions on time? Because from now until 2050, we have like 30 years. Maybe we will not reach it up to there. So we have to think about this. And the last questions, and I think it's reasonable to ask these questions is failure is an option? We might not be able to reach there on time. So there are several key elements of solutions that we can, let's say, suggest. The first thing that we have to do, and I think we should consider this as a, let's say, a temporary solution, is to save energy. Let's try to slow down the depletions of the fossil fuels. Then we will have more time to work finding the way how to solve the problem. The second point is we might need to accept that the world might not be the same as it now. We might have to change our infrastructure. And this might cause also a change of the how do you say, the view of the environment, so on. And another solutions also, it's, and I think Junglab is really concerned, is that we need to find a way how to be financed to do research to in order to help to solve these problems related to energy. Finally, I am really thinking that we should to have a courageous politics, because these problems is not only a Canadian problem or Brazilian problem. It's problems in overall the world. So we should to have let's say a common politics. So as I was saying, we have we have a problem related to energy. We have fossil fuels that is starting to decrease a lot, and soon it's going to be empty. We have also some solutions, but those solutions need to be, let's say, modulate, and we have to solve those problems. The first problems is related to conversions. I have to show to you the example of the bulb and the sequence of conversions, and it's showing to you clearly that we lost a lot of energy when we convert and transport it. The other problems is we also need to find a way how to store efficiently energy that we convert, for example, from the sun into the chemicals in the batteries. But there's one thing that I'm quite sure about, that is that the unique solution is not in the plan. We will need to combine the technology. Uh, we will need to use, for example, a solar cells, and then use another technology and another technology, and put this in batteries. And this is what we need, because just think about the day that there's no wind. How can you use the wind? So you need to find another solutions. Maybe the day that there's no wind, they might have the sun, and vice versa. They may have this the wind today, but not the sun. So we have to combine the energetic technologies. Okay, so there's many advanced materials for for energy that is already known. Junglab is not recreating the scientific world, but we try to use the strategies to help figure out how we can make it more efficient related to the conversion and storage. Let me just drink a little bit of water. I'm coming back. It's I need to. Okay, as I already mentioned, in the few slides, the materials used in the technology device are crucial to have a good conversions and storage. So we can create a good porous materials for example, hydrogen storage. And at UQTR here, you have specialists on hydrogen storage. But we can also use um, create materials and to create some electrode or an electrolyte for batteries. Of course, in this case, we can also think about fuel cells. Fuel cells is interesting. However, the platinum is currently too expensive. So if we can replace the platinum to a cheaper catalyst, this will be awesome. Same thing for the solar cells. We If we are capable to figure out how to make materials that convert the light into electricity in a good, let's say, yield, will be also great. We have also a problem with the price of the solar panels, so we can also work on this field. And nuclear should be also we should to continue actually to use this energy, although it creates a lot of, let's say, side problems, but actually is one of the best options that we have. The only thing maybe what we have to do is to find more abundant fossil fuels for 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 the nuclear. Finally, we can also design some semiconductor to do some photoelectrocatalysis in this case to produce hydrogen, for instance. So this is only few example, and there's much more example than that that could be shown, and you can think about that. But I will just give these examples for today. So now let me start to talk about the Jung Lab and what kind of activity we are doing. When I start my career in 2014, I create a research group that is dedicated to the design of materials, ordered materials, to tackle the energy issue through the design, synthesis, and characterizations of materials that can be useful for energy applications. Currently, the Jung Lab is composed of 13 PhD students and one postdoc, and we all work in different field. Oh, sorry, we all work on different fields of the design of materials for energy, and we try to let's say find solutions related to the conversion and storage. Of course, we have several collaborations, but today I'm proud to say that we are glad and lucky to collaborate with UFAPC. Um, and we also got financial support for our activities, and we are affiliated with several important institute and center that I will talk in few minutes. To do this research activity, we also strongly collaborate with other teams. So Jung Lab has I think a very good environment. We are located at the UQTR in Quebec. Jung Lab is affiliated to the Department of Chemistry, Biochemistry, and Physics. We have several interesting programs. There's more than this, but I just show, let's say, the main program that we have. We have program in chemistry, biochemistry, forensics, physics, material science, and energy. So if you are interested in the future to do some study here, please feel free to contact us, and we will be glad to guide you. We are part of the Institut de Recherche sur l'Hydrogène, which is one of the most important, let's say, institute currently uh, uh, that's try to develop clean and sustainable energy technologies. In this institute, we design materials like my team and the team of my colleague that is today, for example, Jacques Huot. We try also to find a way how to store gas, to separate the gas, and there's also a very strong team on simulations and on utilizations of those materials and technologies. Finally, JungLab is also member of the Centre du Québécois sur les matériaux fonctionnels. The missions of the CQMF is to design functional materials for energy applications. So this is the work environment. I thought that is really important for you to, especially for students. Whenever you think to do research, you really need to think also how to get the best environment as possible to do your research. I think that most of you may already be wondering how do we design materials for energy. Here's a scheme that I often show to my student, as a guideline how to think about an application and how to figure out how to synthesize those materials. Let's imagine that you try to make some catalyst or materials for light harvesting or post materials for storage or materials for batteries, for example. So the first thing you have to do is to think about, okay, what are the molecular components that I needed to in order to get one of these applications here. So you have to think about what kind of element you will add in your starting building block, what kind of functional groups. You have also to think about, okay, let's try to make it as simple as possible, because synthesis can be sometimes very difficult. And also you need to think about, okay, I should to use chemical that it has a low cost, or the process how to get those building blocks should be simple and costless. And then in our field, because I'm seeing in the view of chemistry, we have several strategies how to connect building block together by using the crystal engineering, supramolecular chemistry, or reticular chemistry, hydrogen bond strategy, and coordinations. Finally, when you combine all of this strategy, the chance to get one of the property that you are claiming, it's high, it's quite high, it's feasible, let's say. And the last things also, when you planify to make a materials, try also to see if it's possible to make a materials that can be reusable and can be multifunctional task, let's say. Okay, so in the Jung Lab, we combine several chemical streams, including organic chemistry to create molecules, inorganic chemistry to add properties, because the metals, for example, would give you some magnetism, some redox applications, and several other applications. We also use coordination chemistry to link the unit together. Of course, I already mentioned about the supramolecular chemistry, reticular chemistry, and we also aim the characterizations of the materials in solid state. One of our biggest targets is not only to do research trying to solve directly the problem, because solving a problem can take a lot of time, and we know that we might not be here anymore to see the result. Therefore, we have to think to train younger researchers to develop the materials, because after us they can continue and they can help to solve the problem from now until 2050. Maybe you also questions yourself, okay, why do we need to make ordered materials with well-defined constitutions? Why this is important? So to answer these questions, I am going to show you here. This is one example of the allotrope of carbon. Carbon, let's say it's just an atoms, right? So, but if these atoms of carbon you organize it in three-dimensional, you form diamond. And everyone know that women they love diamond, right? But not only, diamond is not only beautiful as it, but it also has some hardness and has some interesting properties that is already added in some technology even. But if now you take this atom of carbon, instead of to put in three dimension like diamond, you put in two dimension, you are forming graphene. And graphene also has its own properties. Its transparency, it's, let's say, elastic, and it's transparent. And so if you take this graphene and you decide to fold it to itself, you form this nanotube here. And this nanotube also has other properties. Finally, if you take these nanotubes and then you close both sides, you are forming what we call some cage. And here, one of the examples is the C60 with 60 carbon atoms to form this cage. So the property arise from their distinctive structure, from what we see from this example. This is the reason why we design ordered materials. Okay, for I don't really know if everyone has at least a certain background on chemistry. So I decide to give to you a general scheme on the, let's say, three main strategy how to organize matters in materials. So the first one is to use the coordinations chemistry. You create a small, let's say, multi-topic ligands, means that's a ligand that has some coordinations sticky site. And then you mix with metal salt. And if you program it correctly, you might have the chance to form a structure that is porous. And then those type of materials that are crystalline and porous, we call this metal organic framework. And I would use the term MOF uh, after that. So please remember, this is a MOF. And you can also decide to say, okay, I cannot use metals system in the application that I want. So what you can do is to create two, let's say, complementary building block, and then you click them together and form, for example, this type of structure here. Is entirely made with light element like carbon, nitrogen, oxygen, phosphor. And this, we call it covalent organic framework. The third example is it use a hydrogen bond. So you create a molecules that you will add some sticky site by hydrogen bond, and by self-assembling by hydrogen bond, they can form a structure here that I represent. It looks like a diamond. Of course, you can imagine to combine strategy together, huh? And this is what we are doing also in the Jung Lab. So I'm showing you here. Let me show you here one examples that use both coordination bonds and hydrogen bond. So you synthesize these small linkers here, and you coordinate to metals. In this case, it's the palladium. Palladium is quaplanar, and you form this shape here. And then at the end of at the extremity of the molecules, you add some sticky site by hydrogen bond, and this is known to form. This is one type of hydrogen bond that is forming for this sticky site by hydrogen bond. And what you see here, when we solve the structure by single X-ray diffraction, a beautiful structure in two-dimensional, connected by hydrogen bond and coordinations bonds. Those materials are interesting, and the strategy to make those materials are interesting because you can tune the properties of the material by changing the metals. And this it's easy. You just take another metals and take the ligand again, mix it, and produce these materials. And this material, because it contains some transition metals, so it can be used for catalysis. The second example that I would like to show to you is the let's say the synthesis of covalent organic framework for gas storage. So then you can use this tetrahedral compound with a 4 amino group in the extremity of a tetrahedral core, and you can use this building block here with aldehyde group. And if you know a little bit about organic chemistry, you know that when you mix an amine with an aldehyde and then you hit both of these compounds together, you are releasing water, but you form at the same time what we call here the imine bond. Because we put 4 amino group and 2 aldehyde, we can extend the structure and form these beautiful porous materials here. That is the polymer and has a lightweight and it's crystalline, so easy to, let's say, characterize, and you can imagine how to put something in these porous materials. I will not have time to show to you all the work that we have done about that, but you can go read the JAX that we have published in 2013. So this is an overview of the type of ordered materials that we try to design for energy applications. We design porous materials using the coordinations and organic molecules to create these morphs. We also use the covalent bond strategy to create some polymers that can be useful to create electrode of batteries. We synthesize also um, materials that mimic perovskite to uh, to use it for light harvesting. And finally, one of the other materials what we try to do, and this is one of the topics that I'm going to show you more deeply after that, is to create some photocatalyst materials for hydrogen productions. The first thing that I was dreaming with my student when we start to work at the Université de Québec at Trois-Rivières is to develop some photocatalyst materials for hydrogen production. And this is actually, it has been published in Inorganic Chemistry in this year actually. So then it means that we work at least for 5 years, and we were trying to express our dream in this cover page here. The cover page is showing, you know, the brand of our institute, and we hope that when one day our institute will have the chance to have hydrogen stations, and these tanks of hydrogen will be completely filled by by the hydrogen that we will produce with our photocatalyst. Hydrogen are interesting because when you use hydrogen, you only form water as a side product, of course, and energy. Hydrogen is light, so it's interesting when you think about transportation, so on. It has zero emission fuels, and it's has a high power density energy. But the only disadvantage is that this molecules is not directly available as it. So what we have to do is to think how can we produce hydrogen. This is not something new. We will not say that we recreate all research. Young Lab is not recreate all the research, but we use the advantage of what is already known in literature to progress in the field. So we decide to design some photocatalysts to convert the sunlight into chemical bond that is in the hydrogen molecules. And of course, we try also to store the hydrogen. I will not have time to discuss about the hydrogen storage today, but I will certainly discuss about the hydrogen productions. Before I'm showing to you the few of the data, I would like to tell you that photocatalysts are interesting because there's many advantages. It's a green process. It's renewable when you are capable to make a catalyst that you can get back and use it again and use it again. And this photocatalyst can convert the sunlight into chemical energy. And there is a various applications for photocatalysts. You can do water splitting, CO2 reductions, degradations of polluant, disinfections of bacterial, to do some organic compound also for the purpose. So there is many applications. So the first thing that we were trying to do is to look at in the literature what are the most famous, let's say, organic organometallics complex. Sorry. So we found that bipyridine, they have so many applications and also catalysis applications. However, it's not always possible to determine the structure because there is no functional group, so on. So what we decide to do is to replace this bipyridine compound by this deaminothreonine compound. So we just remove one pyridine and put a deaminothreonine group. And then by coordinations with, you can almost do with the whole transitions metals to create this kind of complex that I showed to you here. They are beautiful and interesting for application, but also to study the knowledge in chemistry. We use them to produce hydrogen, and we compare them with the literature, and we found that in most of the case that we have, we can produce higher, not that higher, but higher than what is already reported in literature. I hope that you are capable to see clearly that this one and this one is the mimic of this compound, and this one here is the mimic of this compound, except that in our case, we are capable to add multiple nitrogen atoms that will change the electronic of the compound, but also we have added some amino group, which is not possible to do, let's say, the usual organic chemistry. We have also designed a new type of a complex that is containing amidine functional groups that make the complex stronger. And we found that this one, it's really interesting because it's very stable when we do the photocatalytic activities. If you are really interested on those topics of synthesis and hydrogen productions, you can take this reference here and go look at more in details what we have done in this field. Let me give it to you just an example. Is that we make the first type of complex here, and we found that the tone is not that high, but we were capable to figure out how to increase the tone. The tone is actually the um, um, uh, some value that you use to figure out if your materials are interesting for in this case for hydrogen productions or not. So we found that with this type of amidine complex, the tone is even much more higher. It's like 10 times more than the previous one that we have made. So now, after producing the hydrogen, I would like to talk about the separation techniques and somehow also the gas storage, because you create something, you need to put it somewhere. So I do you remember that during my entire presentations, I I explained to you that there's two processes that is important. You know, the first one is the conversions. This is what I just showed to you, that we were capable to convert the sunlight into hydrogen. And the second one now, I would like to show to you some work that we have done to store the gas, to capture gas also, and separate the gas. Okay, for gas, for separation now, let's take the first picture that I show you here. Is the solid separation. If you can make it crystalline, it's even easier to separate, because you can see the compound. And if they are colorful, then you just try to, let's say, it's difficult, but you can separate them by hands using a microscope, for example. But now, if you have a liquid, two liquid or three liquids, what you can do is to try to do some extractions if they are not miscible, like this picture here. But what's happened now if you have a gas? If you have many gas together, you don't see them, you cannot touch them. So what to do? There's one option is to design pros absorbent for selective capture separations. So this property will depend on how you design your materials. And I'm glad to show to you this front page. We are very lucky and happy that ACS Apply Materials and Interface has selected us to do the front cover for the volumes that they have published recently. So the example, let's take as some example. Let's take this type of gas that you have here, water. It's really important to to have it and to capture. So especially imagine when you are in desert, you need water, so you need to find a way how to capture water. And hydrogen, I already mentioned that this is very important energetic vector. CO2, it's one of the pollutant that we try to capture. And oxygen also, it's one of the vital molecules that we need. So we need to, let's say, separate all of this gas. There's several porous materials that is already very interesting, like zeolite, like metal organic framework, and the covalent organic framework. There's other porous materials, but I would like just to give you these three examples. And today we have tried, oops, it's go too fast. Today, I would like to show you how to prepare metal organic framework. So the first thing, you know, in laboratory, you can use just a vials and then design some ligand, put some transition metals, find a solution that you can dissolve everything together, mix everything together, put in the oven. After putting in the oven, then luckily, if you are lucky, let's say, because you also need to be lucky, it's not only mixing and getting something. If you are lucky, you can get crystals, and from those crystals now you can make a bunch of study on the materials. The first study that we are doing in usually is to do the single X-ray diffractions to get the crystal structure of these crystals here. After that, you can also try to define if your materials, its pores, has um, um, some adsorption properties, so on. So you will do the BET, and you can also study the adsorption to see if you can store gas in your materials. You can also after that study if your material can separate gas. So in order to do that, what do you need to know is that if your objective is to store the gas or separate the gas first, that's the first thing you have to do. And then find the method how to make sure that your your gas and your framework has some interaction like this. I like to show this example of the gecko. How can a gecko can walk everywhere in anyone in the roof zone without falling? Because there is some interactions between his foot and the wall. In his foot, actually, there is some suction cup that can do some, let's say, van der Waals interaction. I don't know if you guys are familiar with van der Waals interaction, but I will give it to you few key points how to figure out whenever we have a good van der Waals interactions or not. Like for example, when you have two aromatic rings, they stack from one to another. This is van der Waals interactions. But when you have also element like nitrogen, oxygen, sulfur, phosphor that has lone pair, this also might help to increase the van der Waals interaction. So what you are going to do is to um, uh, uh, functionalize your materials. Imagine that this house here is your material. You would try to functionalize it with the element that I told you because there's lone pair, so it might increase the interaction between the wall and the gas. You can also try to add more and more aromatic ring is also helping. But what you can do also, if you think about selectivity, you can change, tune the the entrance here. For example, instead of to put a square, you can put in, you can find a way how to make the door triangular or round, and you would discriminate one gas over another one. So there's very many options that we can use to to um, to have some selectivity in this case. So this is the one of the beautiful example that I would like to show. These materials we have called Institut de Recherche sur l'Hydrogène because this material has been created in our institute. So this is also a tradition in morph synthesis. When you make a new morph, you can call it with the name of your institutions or where you have made these materials. So these materials, it's really interesting. First of all, you take this ligand here, you coordinate with metals, and then you would got some crystals, and you take one crystal, you do the single X-ray diffraction, solve the structure, and what we found is that the wall of these materials contain a lot of nitrogen, which is what we want when we think about van der Waals interactions with the gas. The second thing is that the door here, it's square, not that big, and is one dimensional microchannel. It means that if the gas is going in this side, the only exit is the other side. But the point that is also important when you think about materials is that all the crystals that you have made should have the same structure. Remember that the single crystal X-ray diffractions is only solving one crystals. But what's happened with the thousand of the crystals? Are they having the same structure? You don't know. So what you can do is to use the powder X-ray diffractions to define if all the crystals should, if all the crystals have the same structure. So what you can do is to take the single X-ray diffractions, simulate the powder X-ray pattern, and then compare with the experimental one. If you find that it's quite similar, then the chance that the thousand of the other crystals are having the same structure, it's high. The surface area of this type of materials that we have created is not that high. It's only 742 meters square per gram. The anti-void is around 42%. But what is interesting that I will show it later is that we'll have a good selectivity for gas separations. And also one thing that you cannot maybe see clearly here, sorry, because you are not used to see this structure, is that they contain coordinated water that will help us for the selectivity. This is the instrument that my student is using to do the adsorption study. After synthesis, after defining the structure and the texture of the materials, they use this instrument to do the gas, the adsorption study, sorry. The sample, you put it here, and then you have a closed loop, and you can mix the gas here and then study the adsorptions. What we did first is that we have studied the single component gas first. Like in our case, we were interested about carbon dioxide and methane. Carbon dioxide, as you can see here, the uptake is less than 5, but when you look at the uptake of the methane is not higher than 1. This adsorption study suggests that we might have a good materials for gas separations, and then these materials also is capable to capture CO2. So we can use also to solve some issue related to the environment problems related to carbon dioxide. I will not, unfortunately, have time to discuss a lot about that, but I would like to invite you to go look at this article that we just published recently. We have collaborated with other team also to do some simulations, and because we were interested to understand, oh, what is this? Why our materials are so selective? And then we they have used the Grand Canonical Monte Carlo to do this density isocontour, and we found that the CO2 are mainly stick on the wall, and that methane, for example, is not doesn't have any specific positions, and also where you have water, you don't have methane because methane is hydrophobic. So the coordinate water that I was talking to you here, they are interesting for the gas separations and give us a good selectivities. Finally, I have few minutes, so I will just give you two important points. Is that we have made a lot of waste materials, a lot of pollutions. But one of the things that we can do is to reuse these waste materials. So these people, they call also maybe is the new gold. Gold. Like for example, the car tires here can be used to make some component for batteries, and the CO2 that we have created, we can also try to convert to carbon monoxide, to to be used in other chemical reactions. So we can make waste materials into valuable source. Today, I have talked about the energy storage and conversions. I have shown you many examples related to the design of materials. I have also shown you that we can, as a scientist, we can do something to solve the problem. But no matter what we are doing, if we are not educating people to save energy and to teach them how to use properly the energy, we probably will not change that much thing. So I would like to conclude to the fact that okay, we try to solve the problem, but now we have to slow down the depletions of the energy by for example, you are leaving from your home, so try to see if you turn off, if it already turn off all the light. You want to go buy a bread near to you, less than 500 meters, take a bike, don't take a car. If you're at home, you can try to verify, especially for Canadian, verify if all your house has a good isolation in order to keep the heat. Avoid to use boiling water if you don't need it. And also about the household appliance, fill up, fill up until that there's no more space before you start to wash your dishes or your clothes. So this is simple habit, but we can all collectively work together to slow down the problems. So finally, in conclusions, we have designed, JungLab has designed materials for energy applications. We have synthesized new and interesting catalytic materials for hydrogen production and also for other applications such as carbon dioxide reductions. Sorry, not production, but reductions. We have designed capture materials for CO2, but also for gas separations. With collaborations, we also did some simulations to predict the selectivity of our materials from one gas to of another one. And finally, I would like to show you this cartoon because I, I think it's really interesting to have this cartoon here. We are in the world and we face all the same problems. We can solve the problems if we collaborate together. I think this is important to notify, is that together we can solve the problem. Finally, I would like to thank all my students. There is no one that has not made anything. All of them has highly contributed in the Jung Lab, and I'm glad to have them in my team. I would like also to thank all my collaborators like Dr. Hanan, Dr. Wist, Dr. Folivi, Olivier, and Davids. I would like also to thank the facilities that has been given to us, like the lamp at the UDM where we did our photocatalytic study. I would like to thank also ATS Scientific that helping us also with the BET measurement. Of course, I would like to thank all my funding, including Insert, Queen Elizabeth, the UQTR, the Innovation, the Fondation Canadienne pour l'Innovation, sorry, sometimes I speak French, English, RQEI, les relations internationales et francophonie, MyTax, the CQMF, and the ERH. I just would like also to get the chance to mention that the Jung Lab is going to organize an event at the UQTR virtually. It's called the Mini Interdisciplinary Student Symposium. It's going to be on the 26th of March 2021. So we will be glad to have you guys assist to our meeting. and if you would like to give a presentation, please feel free to contact me, and I will give you all the details how to apply for a 15 or 12-minute presentations. Finally, I would like to thank everyone, and one more time, thank you to the Young Lab. I really hope that you like the presentation. It's quite hard, to not see students, to not see the expressions, because when I share my screen, I don't see anyone. It's like I talk alone.
Yes,
I really hope that you guys enjoy the talk, and I will be glad to discuss with you about the project we do related to energy.
yes, for sure. I believe everybody enjoyed it a lot. I have a question. I believe I can start with a question.
Yes, you can.
Um, First, thank you very much. And always that I see the hydrogen considered as a possible fuel and a possible source of energy.
Yes.
I've always think about the problem with the explosions and the dangers of this. So I don't know if you mentioned that, but how these materials and how this combination can provide more security for this source of energy.
Yes, this is really interesting questions actually. This is not something that we work directly, but in my institute, for example, there is specialists that it's working on simulations to see how the gas is going, and so on. So they are really specialists on this. But usually, if you know how to handle something, you should not have any problems. If there is problem, it's mean that there's an issue that you didn't check correctly. I'm telling you that hydrogen might be is dangerous, yes, but water can be dangerous also. you know you have a swimming pool, you have a kids that don't know how to swim. The kid fall on the swimming pool, he can die also. So you need to put the necessary security to prevent this. I hope that I answered to the questions. But for sure, you need to do a lot of study to make sure that you will keep everything safe.
Yes, for sure. Because when I saw the draw with those tanks of hydrogen,
Yeah,
I
yeah.
was thinking, oh my god, and the security about that. But yes, I agree with you. Thank you very
You know,
much.
in there's a lot of university that also have a big tank like that of not hydrogen but nitrogen. Nitrogen can be also very dangerous, especially when it's a liquid nitrogen. So they just make sure that they design correctly let's say the reservoir, and they make all the necessary to prevent the accident.
Yes, I was just wondering if some material, the interaction of some material with the hydrogen could prevent some accident or prevent the explosions.
I guess yes, you can design. This is actually an interesting topic. If you can design materials that can store the gas, but also, let's say, uh, inhibit the gas before you release
Yeah.
it and use it, this will be perfect. I think it's a good question. It's interesting.
Yes, Professor Ennis is back.
Hi, Anna.
Hello, everybody. I'm so sorry. My internet today is very, very bad. I couldn't get my connection at the computer. I'm now at my cell phone, but it's
I
good that
understand.
you were able to go on. I would like
Yeah.
to thank Adam for his excellent presentation. And as I see, the questions are already going on, so
uh,
please continue.
well, thank you so much to give me the chance to virtually travel to UFABC, because I have I consider that UFBC is my second home. You know, I really like to be there to do science, to share the knowledge with a student. And this is not my first time that I'm giving a lecture for UFABC. And I hope that this will not be the last one.
Of course, it will not be the last one.
Yeah. Any other questions?
Shy, everybody.
I have one more question.
Yes.
You've mentioned some scientific articles that you've published a lot.
Yes.
Congratulations.
Thank you.
Do you deposit some patent?
No, we didn't do any patent. We hope that one day we will have some patent, but for now, we think that we are not just ready for this, and we like to publish because we would like to share our knowledge
Yeah.
also to scientists, because our idea is to we might not be able to solve directly the problem, but we can contribute in solving the problems. So we try to 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 learn things and to train younger students to continue the work. I just want to
Okay.
say to students, if you have some trouble with English or French, you just speak in your language and we will translate the questions. Okay, so feel free to ask questions. I would be glad to try to answer.
Perfect. Thanks.
Thank you so much.
Adam, first, thank you for your lecture. Yeah, congratulations for your works. And I have a question about you talk about, you commented about metals and organic compounds, yes?
Yes,
like
yes.
polymers. Ceramics have a potential for this type of application?
Yeah. No, definitively. You know what? I have just showed to you today, let's say, a few kinds of few type of materials. But for me, ceramic also has some potential for applications. They can be used as a support, for instance. So for me, any kind of materials interests me. If I see the way how to use it, how to functionalize it, I definitely would use. So that's why the Jung Lab, it's it's very focused, but at the same time it's very large. We would like to touch to all kind of materials to design materials for energy application. This is our only one focus, but all the materials. We are not only just focusing on morph or on molecular catalyst. All kind of materials that is useful, we will use it.
Yeah, sure. I answer about ceramic because naturally this kind of materials, these porous, yes,
Yeah,
have a high porosity.
yeah,
Then I think it have a potential to.
absolutely. Absolutely. And if any of you would like to collaborate with Jung Lab, please feel free to contact us. We will be glad to see how we can collaborate together. Because alone, we cannot do anything. It's exactly like the last picture that I showed to you with people with a long spoon. You cannot put the long spoon in your mouth, but you can easily put to your neighbors. So if we share knowledge and we work together, we will progress.
Yeah, thank you.
You're welcome.
So,
Please.
Yes.
Hi, sir. I have a question, sir.
Yes.
In the slide where you showed the normal complex and the median complexes.
Yes.
Yeah. My question is why there is an increase in hydrogen production when you go from normal complexes to the median complexes?
Very good question, Sanin. Actually, we don't know exactly, but we know that when we functionalize to amidine group, we got a better photocatalytic activities. See, maybe because there is some more, let's say, conjugation systems, or maybe because it's that our complex is much more stable. You know, actually, we didn't, but because this is also part of your work. So you know also that we didn't study deeply the, the exact mechanism that we have for the photocatalytic activities.
Okay, so thank you. Thank you.
You're welcome.
Adam, I lost a part of your talk because of my internet.
Yeah.
But so if my question is not good, I'm sorry.
No, no, no,
But
no, please.
you convert the energy, then you storage the energy, and how do we do to get the energy back when we want to use it? Is it something that you think when you think about the storage? Of course, I think it is, but
Anna, this is it's you know what, you give me a very deep questions, actually, very deep question. This is something that everyone try to solve also. You know, the storage is something very difficult to do, but the let's say the disruptions is also something difficult to do sometime, because sometimes you really need to heat so on to release the gas. But something that I have not shown, um, and I have not explained fully in my talk, is that our adsorption study we did at room temperature and room, let's say, atmospheric pressure. It means that you can absorb the gas and desorb it without not really heating too much. That is really interesting. But we still have other problems. Is that our materials don't have the highest uptake. It's not, the uptake is not that high. So it's like a compromise. We need to figure out how to make a materials that absorb more, but maybe we will lose a little bit the selectivity and vice versa. So there's a lot of work behind this, actually. I I, I, I will tell you that we are working on this. We work on this, actually, this issue that you are just raising. It's too deep.
okay, thank
Yeah.
you.
Thank you for your question.
Well, Adam, I'm sure everybody's full of questions, but
Mm.
you have presented so many informations that are being processed in everybody's minds.
Okay.
So I would like to thank you for your very nice presentation. I would like to invite you to come to Brazil whenever you want,
Thank you so much.
and to collaborate with us, not only with Pacato and Sydney.
Yeah, for sure, for sure. I'm thinking that more we are, the more we can solve problems. So, guys,
Yeah,
if you're interested on anything about Young Lab, please feel free to contact me. And of course, if you are planning to do other study outside from Brazil, we will also welcome you. So, don't you have my emails? You know where I am. Just feel free to contact me, and we find a way how to bring you here. I
the
have
same for your students
yeah, yeah,
to come here whenever
absolutely.
the pandemic is over, because I don't know exactly where it will, when it will be.
I am planning. I'm planning to bring the best student in my team in your university to do some research for several months. So please be aware about that and help us to do that, because this is going to build us to a new, let's say, a level of research. You know, when we
Yeah,
share science, is going to be helpful for everyone. So if there is no more questions, I would like to thank everyone, and hope to see you in the near future. Thank you so much. Thank you. Have a good night. Bye
thank you.
bye.